Newtonian mechanics is where the modern story of physics begins. It's a branch of classical mechanics that describes the motion of objects under the influence of forces, formulated in the 17th century by Sir Isaac Newton. Imagine it as the physics of everyday life, the reason you can throw a ball and predict almost instinctively where it's going to land. It's how we can calculate the path of planets, predict the time of sunrise tomorrow, and launch rockets into space. At its heart, Newtonian mechanics boils down to a few simple laws. Laws that change the way we understand the universe. Let's start with Newton's first law, sometimes called the law of inertia. An object at rest stays at rest, and an object in motion stays in motion unless acted upon by an external force. This means that if you were to kick a ball across a perfectly smooth, endless surface, it would keep moving forever. Of course, that doesn't happen in real life because of forces like friction, which gradually slow it down. But in a vacuum, with no resistance, the ball would keep rolling eternally. This simple observation, that objects maintain their state unless interfered with, was revolutionary. Before Newton, many believed objects naturally slowed down and stopped due to their own qualities. But Newton showed us it was forces, or lack thereof, that dictated motion. Newton's second law connects force, mass, and acceleration. F ma. This is probably the most famous formula in all of physics, and it's incredibly intuitive once you break it down. See, if you have a heavy boulder and a small pebble, the same push won't make them move in the same way. The boulder, with its greater mass, would require far more force to achieve the same acceleration as the pebble. This law is not just theoretical. It's the reason why engineers can calculate how much fuel a rocket needs to reach a certain speed, or why designers can determine how fast a car can accelerate based on its weight and engine power. Finally, Newton's third law states, for every action, there is an equal and opposite reaction. When you push against a wall, it pushes back with equal force. This law is evident in all interactions. Think of a rocket engine. As the engine expels exhaust gases in one direction, the rocket itself moves in the opposite direction. Or picture a swimmer pushing water backward to propel themselves forward. Newton's third law encapsulates the way the universe balances forces. One of Newton's crowning achievements was the universal law of gravitation. It states that every mass attracts every other mass with a force that's proportional to the product of their masses, and inversely proportional to the square of the distance between them. Simply put, if you double the mass of an object, the gravitational pull it exerts also doubles. If you double the distance between two objects, the gravitational force weakens to a quarter of its original strength. This law applied not just to apples falling from trees, but also to planets orbiting stars and moons orbiting planets. Newton's law of gravity allowed people to understand why planets orbit the sun in predictable paths. It explained the behavior of tides, the orbits of moons, and even the path of a cannonball shot from a hilltop. The same force pulling an apple to the ground is also what keeps the moon in orbit around the Earth. This concept, that a single predictable force governed the motions of everything from small objects on Earth to celestial bodies in the heavens, was nothing short of radical. Newton essentially unified the heavens and Earth under one rule, a revolutionary concept at the time. The impact of Newtonian mechanics extends beyond science to engineering, space exploration, and even day-to-day activities. For example, knowing that force equals mass times acceleration lets engineers design airplanes and predict how they'll respond to various atmospheric conditions. Newton's laws also govern the way we construct buildings, ensuring they can withstand forces like wind and earthquakes. Calculations derived from Newtonian mechanics are the reason why structures can be built taller and stronger than ever before. Space exploration would be impossible without these principles. When scientists calculate the trajectory of a spacecraft, they're using Newtonian mechanics to chart the course. They must consider the gravitational pull of various planets and celestial bodies, and use the laws of motion to understand how different forces will alter the path of the spacecraft. Even though today's physics incorporates more advanced theories, Newtonian mechanics remains the basis for understanding most of these movements on a practical level. Newtonian mechanics works remarkably well for most everyday purposes. However, as scientists started examining things on extremely small or large scales, they noticed its limitations. When objects move at speeds close to the speed of light, or when they exist within intense gravitational fields, Newton's laws don't fully apply. This is where Einstein's theory of relativity comes into play. Likewise, at the atomic and subatomic scales, quantum mechanics takes over, as Newton's laws can't account for the strange, probabilistic behaviors of particles. Despite these limitations, Newtonian mechanics remains one of the most robust frameworks in science. It may not explain everything, but it explains a lot with impressive precision in the world we interact with daily. Newton's laws of motion and gravitation continue to serve as the bedrock of engineering, mechanics, and classical physics. In many ways, Newtonian mechanics reflects the power of simplicity. A few basic laws govern an astonishingly wide range of phenomena. Newton's work shows that complex motions and interactions can be understood through simple principles, a lesson that laid the groundwork for the more intricate theories that followed. Thermodynamics. At its core, thermodynamics is the study of energy, heat, and work, and how these elements interact in physical systems. Imagine thermodynamics as the science of change. It's all about understanding how energy moves and transforms in everything from engines and refrigerators to stars and black holes. It provides rules for what's possible and impossible in our universe, from why a cup of coffee cools down over time to why we can't build a perpetual motion machine. To truly grasp thermodynamics, let's explore its four fundamental laws, each of which adds a new layer to our understanding of how energy operates in the world around us. The zeroth law of thermodynamics, though often overlooked, lays the groundwork by defining what temperature is and how it can be measured. Imagine three objects. If object A is in thermal equilibrium with object B, and object B is in thermal equilibrium with object C, then A and C must also be in thermal equilibrium. This transitive property is what allows us to say that two objects at the same temperature, even without touching, will not exchange heat. Think of the zeroth law as the rule that makes thermometers meaningful. If you place a thermometer in a glass of water, you can trust the reading because the thermometer reaches thermal equilibrium with the water. This law may seem simple, but it underpins our ability to measure temperature consistently and reliably. The first law of thermodynamics is essentially the law of energy conservation, stating that energy cannot be created or destroyed, only transformed. It tells us that the total energy in a closed system is constant. Imagine you're pushing a boulder up a hill. Your work, input energy, is stored in the boulder as potential energy. If you let it roll down, that potential energy transforms into kinetic energy as it gains speed. In other words, energy flows and changes forms, but the total amount remains constant. This law is the reason why you can't get more energy out of a system than you put into it. It's a fundamental limit on what's possible in engineering and physics. For instance, in an internal combustion engine, the chemical energy in gasoline is transformed into heat, which then transforms into mechanical work to power your car. But some energy is always lost as waste heat. It's not destroyed, but spread out in a less useful form. The first law essentially tells us that all processes involve energy transformations, but we can never get something from nothing. If the first law is about the conservation of energy, the second law of thermodynamics introduces us to the concept of entropy. Entropy is a measure of disorder or randomness, and the second law states that the total entropy of an isolated system can only increase over time. Yes, sir. This principle gives us what's known as the arrow of time, a clear direction in which time flows. Imagine a deck of playing cards. If you shuffle it thoroughly, the order becomes more random, an increase in entropy. Reversing that process, returning the deck to a perfectly ordered state through random shuffling, is practically impossible. Similarly, if you spill cream into your coffee, the two will mix together, increasing the disorder. It's nearly impossible to separate them again. The second law also explains why heat naturally flows from hot objects to cold ones. When you put a hot mug of tea in a cooler room, the heat flows outward, increasing the overall entropy as the tea cools and the room slightly warms. This law is what makes perpetual motion machines impossible. They would violate the natural increase of entropy in a closed system. In other words, every energy transformation has an inherent cost. Some energy will always be lost to entropy. The third law of thermodynamics is perhaps the most abstract, but equally profound. It states that as the temperature of a system approaches absolute zero, 0 Kelvin or minus 273.15 BGC, the entropy of the system approaches a minimum value, usually considered zero. Absolute zero is the lowest possible temperature, where all atomic motion theoretically stops. While it's impossible to reach absolute zero exactly, this law helps scientists understand the behavior of systems at extremely low temperatures. At temperatures near absolute zero, materials start to behave in strange and unique ways. For instance, certain materials become superconductors, allowing electricity to flow with zero resistance. The third law also implies that you can never quite reach absolute zero because removing that last bit of heat becomes exponentially harder as you approach it. Thermodynamics is woven into the fabric of everyday technology and natural processes. Refrigerators and air conditioners, for instance, operate on cycles that leverage principles of thermodynamics. They extract heat from a cooler area and release it into a warmer one, which seems counterintuitive until you understand that they're driven by an input of work, usually in the form of electricity. Another example is the steam engine, one of the earliest and most impactful applications of thermodynamics. In a steam engine, water is heated to produce steam, and this high-pressure steam drives a piston, turning heat energy into mechanical work. Understanding the limits of efficiency in these engines paved the way for more advanced and efficient machines, from cars to power plants. Thermodynamics is also critical in understanding astrophysics and the life cycle of stars. Stars burn their fuel through nuclear fusion, a process that releases an enormous amount of energy, but also generates entropy. Eventually, as stars exhaust their fuel, they undergo transformations, expanding into red giants or collapsing into white dwarfs, neutron stars, or black holes. This progression follows the principles of thermodynamics, where energy transformations and entropy drive the life cycle of these celestial bodies. Thermodynamics doesn't just describe mechanical systems. It applies to any system where energy changes occur, from biological organisms to cosmic events. At its essence, thermodynamics gives us a structured view of why energy changes are often irreversible and how energy disperses in systems, providing both elegance and limits to what we can achieve. By showing us the boundaries of efficiency and the inevitability of entropy, thermodynamics also serves as a reminder of the universe's irreversible nature. In a sense, these laws mirror life itself, structured, dynamic, and governed by change. And while we can't violate these laws, we can manipulate them within their constraints, creating technology that harnesses the power of energy while acknowledging the inevitable costs. Thermodynamics is a beautiful balancing act between energy, heat, and work, revealing the invisible rules that govern everything, from the simplest cup of coffee to the engine of the cosmos, electromagnetism. Electromagnetism is a fundamental force of nature, responsible for everything from the light that illuminates our world to the power that drives our technology. It's the dance between electric and magnetic fields, woven into the fabric of our universe and governing how charged particles interact. Imagine it as the invisible yet omnipresent force shaping much of what we experience daily, from magnets clinging to refrigerators to the devices we carry in our pockets. To understand electromagnetism, let's break it down into its key components: electric fields, magnetic fields, and the principles that link them together. This story of electric and magnetic forces began with ancient observations and culminated in a unified theory that changed the course of physics. The story of electromagnetism begins with electricity. Ancient Greeks noticed that when they rubbed amber against fur, the amber could attract small objects like feathers. This strange phenomenon was an early encounter with static electricity, an electric charge built up by friction. Today, we know that electric fields originate from electric charges, which come in two types: positive and negative. When charges accumulate on an object, they create an electric field, a region of influence that can exert a force on other charges. Picture electric charges as tiny actors on a stage, each with a role. Positive and negative charges are like opposing characters. They attract each other, whereas like charges repel. This attraction and repulsion are governed by the electric field, which radiates outward from any charged object. The strength of this field determines the force exerted on other charges within it. This is why a balloon rubbed on your hair can stick to a wall. Its surface has accumulated charge that interacts with the charges in the wall's surface, creating an attractive force. While electric fields come from charges, magnetic fields arise from moving charges, specifically those that flow electric current. Ancient civilizations discovered magnetism through lodestones, naturally occurring magnetic rocks that could attract iron. But it wasn't until the 19th century that scientists like André-Marie Ampère and Michael Faraday unraveled the connection between electricity and magnetism. Imagine magnetic fields as lines that loop around current-carrying wires, somewhat like ripples created by a stone thrown into water. These magnetic lines form closed loops, always finding a way to return to their source. Magnets, like the ones you see on refrigerator doors, are permanent sources of magnetic fields. Inside these magnets, tiny atomic particles called electrons are moving in a way that aligns them and creates a stable magnetic field. The most fascinating thing about magnetism is that it isn't isolated. It's inherently linked to electricity. Wherever there's electric current, there's a magnetic field. And this connection is a cornerstone of electromagnetism. The unity between electric and magnetic fields was first proposed by Michael Faraday. He discovered that a changing magnetic field could induce an electric current in a nearby wire, a phenomenon now known as electromagnetic induction. Imagine a magnet moving through a coil of wire. The changing magnetic field generates a current in the wire. This discovery forms the basis of electric generators, which convert mechanical energy into electrical energy by moving a magnet near coils of wire. Electromagnetic induction is the reason we have electricity today. The rotating turbines in power plants work on this principle, transforming the kinetic energy from wind, steam, or water into electric energy, which flows through power lines to our homes and cities. Faraday's work showed that electric and magnetic fields are two sides of the same coin. Where there's one, there's the potential for the other. The true breakthrough came when James Clerk Maxwell formulated his famous equations, 4 mathematical statements that united electric and magnetic fields into a single framework. Maxwell's equations describe how electric charges and currents create electric magnetic fields, and they reveal that changes in these fields can propagate as waves. Imagine a moving charge creating a ripple in the electromagnetic field, much like a pebble dropped in a pond. This ripple travels outward at the speed of light. Maxwell's equations showed that light itself is an electromagnetic wave, a fluctuation of electric and magnetic fields traveling through space. This discovery was revolutionary, as it linked visible light to a vast spectrum of electromagnetic radiation, including radio waves, microwaves, X-rays, and gamma rays. The implications were profound. Light, radio signals, and all forms of electromagnetic waves were simply different frequencies of the same underlying phenomenon. The entire electromagnetic spectrum became a new frontier, enabling technologies like radio, television, radar, and even Wi-Fi, which all operate using specific frequencies in this spectrum. Electromagnetism is responsible for nearly every modern technology. Electric motors rely on the interaction between electric currents and magnetic fields. In a motor, electric current flows through coils, generating a magnetic field that interacts with permanent magnets, creating rotation. This principle powers everything from household appliances to electric cars. Transformers, another application of Faraday's induction principle, allow us to efficiently transmit electricity over long distances by stepping up the voltage for long-distance transmission and stepping it down for safe household use. Transformers make our power grids viable. On a smaller scale, electromagnetism governs the behavior of atoms and molecules, shaping the structure of matter. The way electrons orbit an atomic nucleus and interact with other atoms relies on electromagnetic forces, as do the bonds that form between atoms and molecules. This is why chemistry exists at all, because electromagnetism holds matter together and dictates how atoms can combine. With the advent of quantum mechanics, our understanding of electromagnetism gained new depth. In quantum theory, electromagnetic interactions are mediated by particles called photons, which are essentially quanta of light. When two charged particles interact, they exchange photons, which carry the electromagnetic force between them. This quantum perspective explains why electromagnetic forces are incredibly strong and able to act over vast distances. Compared to gravity, electromagnetic forces are responsible for nearly all phenomena we experience directly. Chemical reactions, material properties, and even the way our eyes perceive light all stem from electromagnetic interactions. In a way, this force shapes our everyday reality more than any other. Electromagnetism, with its intertwining electric and magnetic forces, is one of the most studied and utilized forces in physics. It bridges the macroscopic world we experience and the microscopic world of particles and photons, bringing coherence to everything from simple magnets to the most advanced telecommunication. Its principles have transformed our world, enabling us to harness energy, communicate over vast distances, and explore the atomic and cosmic scales. Through electromagnetism, we've learned that even the invisible forces around us have an elegance and consistency that reveal the underlying beauty of our universe. And as we continue to explore the limits of electromagnetism, from quantum computing to medical imaging, we see just how profoundly it shapes and enables the unfolding story of human progress. Special relativity. Special relativity, formulated by Albert Einstein in 1905, revolutionized our understanding of space, time, and motion. Before Einstein, scientists believed that space and time were fixed, absolute frameworks within which objects moved. But Einstein showed that these seemingly concrete notions are in fact interconnected and flexible, transforming how we view reality itself. Imagine you're standing on a train platform, watching a train zoom past at an incredible speed. For you, time feels the same as ever. You can feel each second ticking by. But for someone on board the train, moving at high speed, time might actually feel different. This concept, that time can stretch or shrink depending on the speed at which one is traveling, is one of the core ideas of special relativity, often referred to as time dilation. To understand how special relativity works, it helps to start with Einstein's bold assumption. The speed of light is constant, regardless of whether you're moving toward or away from a light source. Light always travels at a fixed speed of about 300,000 kilometers per s. This might seem strange at first because we're used to thinking that speed should add up. If a car speeds toward you while you're walking toward it, the car's speed would seem faster from your perspective. But light doesn't follow this logic. It remains constant regardless of any observer's motion. This constancy of light speed forces us to rethink the structure of space and time. Imagine that the speed of light is like a universal speed limit. No matter how fast you go, you can never exceed or even match this speed. But what happens as you get closer to it? One of the most mind-bending predictions of special relativity is time dilation. Picture two twins. One stays on Earth while the other travels in a spaceship close to the speed of light. According to special relativity, the twin on the spaceship would experience time more slowly than the twin on Earth. If the astronaut twin returns to Earth, they would find their sibling has aged significantly more. This phenomenon, often called the twin paradox, isn't just theoretical. Scientists have confirmed time dilation experimentally using precise atomic clocks in high-speed jets and satellites where clocks in motion run slightly slower than those on Earth. The reason for time dilation lies in the relationship between time, space, and the speed of light. If light speed is constant, then space and time must adjust themselves for different observers. At high speeds, time slows down to ensure that everyone still measures light moving at the same pace. So while time feels norm to each individual, the rates at which time flows are not absolute. They depend on the observer's velocity. But special relativity doesn't just affect time. Space itself is also flexible, a phenomenon known as length contraction. According to this principle, objects traveling near the speed of light appear shorter along the direction of their motion. Imagine you're observing a spaceship hurtling by at close to light speed. To you, the spaceship would appear squished in the direction it's moving, almost like an accordion. The faster it goes, the more it appears to contract. This contraction isn't a trick of perception. It's a real physical effect due to the interwoven nature of space and time. In the astronaut's frame of reference, everything seems normal. They don't feel any shorter or squished. But from the viewpoint of an outside observer, space has adjusted to accommodate the constant speed of light. Another counterintuitive concept in special relativity is simultaneity. The idea that two events happen at the same time is not universal. Suppose two lightning bolts strike either end of a moving train. An observer standing on the platform may see both bolts strike simultaneously. But an observer on the train might see one bolt strike before the other. This isn't because of any delay in perception, but because the concept of simultaneous is relative. It depends on the observer's motion. This relativity of simultaneity illustrates that there is no single universal now that applies to everyone. For us on Earth, now might mean October 26, 2024, at 3 p.m. But for someone on a spaceship hurtling through the cosmos, moving close to the speed of light, what constitutes now might differ from ours. In the vast tapestry of space and time, what one observer considers as present can be the past or future for another. One of the most famous outcomes of special relativity is the equation EMC2, which links mass and energy. In this equation, E represents energy, M represents mass, and C is the speed of light. It suggests that mass and energy are interchangeable. They are two forms of the same thing. This concept is not just theoretical. It's the reason nuclear reactions produce such tremendous energy. In atomic bombs and nuclear reactors, a small amount of mass is converted into a massive amount of energy. The equation tells us that even a tiny amount of mass, multiplied by the square of the speed of light, can release vast amounts of energy. Special relativity thus reveals a deep connection between matter and energy, showing that mass itself is a form of potential energy. Special relativity might seem esoteric, but its effects are woven into our daily lives. For example, the Global Positioning System, GPS, relies on a constellation of satellites orbiting Earth, each equipped with highly accurate atomic clocks. These satellites move at high speeds relative to the surface of Earth, which means that, according to special relativity, time ticks more slowly for them. Engineers must correct for these relativistic time differences. Otherwise, GPS readings would be wildly inaccurate, placing you miles from your intended destination. The principles of special relativity also influence other technologies, such as particle accelerators. When particles are accelerated to near light speeds in machines like the Large Hadron Collider, their mass effectively increases, requiring more energy to accelerate them further. This effect is a direct consequence of special relativity, shaping the design and function of cutting-edge scientific equipment. Special relativity challenges our intuitive sense of time and space, suggesting that they are not rigid backdrops, but flexible and responsive. It reveals a universe where time and space are woven together, where the notion of simultaneity dissolves, and where even mass and energy are deeply intertwined. In a way, Einstein's theory invites us to expand our understanding of reality, to think beyond the familiar and accept that the universe operates in ways that often defy common sense. This is one of the most remarkable aspects of special relativity. It pushes the boundaries of human perception and invites us to explore the vast, interconnected fabric of the cosmos with fresh eyes and a sense of general relativity. Imagine you're standing in an elevator and suddenly the cables snap. The elevator starts to plummet, and for a brief moment, you feel weightless, as if gravity has disappeared. This simple experience is at the heart of Einstein's general theory of relativity. Einstein, looking for answers about the universe's structure, realized that gravity might not be a force pulling objects together, as Isaac Newton once thought, but rather the result of how objects move within the very fabric of space and time. In our everyday life, we tend to think of space as a flat and unchanging grid, like graph paper. But Einstein envisioned space differently. He saw it as a flexible, bendable fabric. Space and time are interwoven, forming space-time that can curve, stretch, and warp in response to mass and energy. When a massive object like a planet or a star sits in space-time, it creates a dent, causing smaller objects nearby to fall into it. To picture this, Imagine placing a bowling ball in the middle of a trampoline. The weight of the ball stretches the trampoline, forming a depression. If you roll a marble near the edge, it will spiral toward the bowling ball. Not because the bowling ball is pulling it in, but because the shape of the trampoline guides the marble's path. Similarly, Earth warps the fabric of space-time, and the moon orbits Earth not because of a literal force pulling it inward, but because it is following the curved track created by Earth's mass. Einstein's general relativity redefined gravity as the curvature of space-time itself. This approach was revolutionary, flipping the traditional view of gravity on its head. Under general relativity, massive objects tell space how to curve, and curved space tells objects how to move. This framework is beautifully summarized in the phrase, matter tells space how to curve, and space tells matter how to move. Einstein's insight was groundbreaking, but he didn't stop there. He developed mathematical equations to describe this curvature, known as the Einstein field equations. These equations are complex but elegant, capturing how mass and energy dictate the structure of spacetime. In regions with intense gravity, such as near black holes, these equations predict extreme curvatures, leading to phenomena that defy common sense, like time slowing down or light being bent. One of general relativity's most surprising predictions is that gravity affects time. Time flows more slowly in stronger gravitational fields. This effect, known as gravitational time dilation, means that time passes more slowly on Earth's surface than it does in space, far from any massive objects. This isn't merely a theoretical concept, it's measurable. Imagine you're wearing a pair of watches, one at your ankle and one on your wrist. Because your ankle is closer to Earth's center, it feels a stronger gravitational pull, and time runs a bit slower there than at your wrist. The difference is tiny but real, and it accumulates over long distances and extreme gravitational fields, such as near a black hole where time essentially freezes for an outside observer. A century after Einstein published his theory, one of his predictions, gravitational waves, was finally observed. Einstein proposed that massive, accelerating objects like merging black holes or colliding stars would create ripples in spacetime. These gravitational waves spread outward like ripples on a pond, carrying energy across the cosmos. In 2015, scientists at the LIGO Observatory confirmed this prediction by detecting gravitational waves from two merging black holes, a discovery that opened a new era of astrophysics. Gravitational waves allow us to observe cosmic events we previously couldn't, providing a way to listen to the universe's most dramatic collisions. The confirmation of gravitational waves has been one of the most profound validations of general relativity, proving that space-time is not only flexible, but can ripple and vibrate. Black holes are perhaps the most extreme manifestations of general relativity. When a star collapses under its own gravity, it can compress into an object so dense that it warps space-time into a point known as a singularity, where density becomes infinite and the usual laws of physics break down. Surrounding this singularity is the event horizon, a boundary beyond which nothing, not even light, can escape. The concept of black holes challenged the boundaries of scientific imagination, but general relativity predicted their existence decades before astronomers observed them. In 2019, the Event Horizon Telescope captured the first ever image of a black hole's event horizon, confirming yet another aspect of Einstein's theory. Black holes highlight general relativity's power to predict phenomena far beyond human intuition, revealing mysteries that remain largely unsolved even today. It might be tempting to think of general relativity as something distant, affecting only stars and galaxies, but its principles influence technology we use every day. The Global Positioning System, GPS, which relies on satellites orbiting Earth, must account for both special and general relativistic effects to work correctly. Due to both the satellite's speed and their distance from Earth's gravity, their onboard clocks tick slightly faster than clocks on the ground. Without relativistic adjustments, GPS calculations would be inaccurate, placing you miles away from your actual location. This practical application shows that general relativity is not just a theoretical concept, but an integral part of our understanding of reality. It governs everything from cosmic evolution to the precision of modern technology, seamlessly bridging the cosmos with daily life. General relativity doesn't only provide equations, it reshapes our understanding of the universe by showing that space-time is flexible and interactive. Einstein offered a framework that has inspired generations of physicists and cosmologists to look deeper. General relativity paved the way for our study of black holes, the Big Bang, and even the nature of time itself. Despite its monumental success, general relativity isn't the final answer. At the quantum level, where particles behave unpredictably, general relativity doesn't hold up. The quest to unify general relativity with quantum mechanics into a theory of quantum gravity remains one of the biggest open questions in physics. It's a testament to Einstein's genius that over a century later, his ideas continue to push us toward new horizons, challenging us to understand the mysteries of space-time and the very fabric of the cosmos in quantum mechanics. Basics. Picture a world that doesn't obey the rules we see every day. This is the world of quantum mechanics, where particles can be in multiple places at once, seem to make decisions randomly, and influence each other instantaneously across great distances. Quantum mechanics is the branch of physics that seeks to explain and predict the behavior of particles at the smallest scales. It's the science of the supersmall, where particles like electrons and photons reveal surprising and sometimes counterintuitive truths about reality. The quantum world deals with particles smaller than atoms. To get a sense of scale, imagine dividing a single grain of sand in half, then keep dividing it until you reach a point where the pieces are no longer even matter as we know it, but fundamental particles like quarks and electrons. Here, traditional physics stops working in expected ways, and new rules take over, rules that defy common logic. One of the first mysteries that quantum mechanics tackled was the dual nature of light and matter. Light, which we see every day and which helps us navigate our world, behaves as both a wave and a particle. This idea was initially tested to the famous double-slit experiment. In this experiment, light particles or photons are fired at a screen with two narrow slits. If we cover one slit, photons behave like tiny pellets, forming a pattern behind the open slit, just as you'd expect. But when both slits are open, the photons create an interference pattern, something only waves should produce. Even stranger, if we fire single photons through the double slits one at a time, they still form an interference pattern over time, as if each photon somehow knows about both slits. This dual nature isn't limited to light. Matter itself, like electrons, also shows wave-particle duality. This discovery was one of the first clues that the quantum world behaves in ways far outside our everyday experience. In classical physics, we can measure things with great precision. If we know the speed and position of a car, we can predict exactly where we'll be a few seconds later. But quantum mechanics doesn't allow such certainty. Werner Heisenberg's uncertainty principle tells us that we cannot simultaneously know a particle's exact position and momentum with absolute accuracy. The more precisely we measure one, the less precisely we know the other. Imagine trying to grab a bouncing basketball in a dark room. You can hear where it is and make a guess, but you can't pinpoint its exact location and speed at the same time. This uncertainty isn't due to limitations in our measuring tools. It's a fundamental aspect of reality at the quantum level. Particles don't have defined properties until they're measured, and this unpredictability is woven into the fabric of quantum mechanics. One of the most intriguing aspects of quantum mechanics is superposition. Particles like electrons exist in multiple states simultaneously until observed. To make sense of this, physicist Erwin Schrödinger proposed a thought experiment known as Schrödinger's cat. So, imagine a cat in a sealed box with a device that has a 50-50th chance of releasing a poison. Until we open the box, the cat is both alive and dead, a superposition of states. Much like quantum particle, once we look, the state collapses into one outcome, alive or dead. This phenomenon has been proven with particles. Electrons, for example, can be in different places at the same time, a reality we only recognize when we observe or measure them, forcing them to choose one location. The act of measurement in quantum mechanics is like a spotlight. It forces particles to reveal a single outcome from multiple possibilities. Quantum mechanics also reveals that particles can become entangled, meaning their states are linked even if separated by vast distances. If we have two entangled electrons and we measure one, the other instantly reflects this measurement, no matter the distance between them. Albert Einstein famously called this spooky action at a distance, because it seems to defy the speed of light limit. Though it challenges our intuition, entanglement has been confirmed through numerous experiments, suggesting that particles are somehow connected in a way we do not yet fully understand. Entanglement has practical applications in the field of quantum computing and secure communication. Quantum computers use the principles of entanglement and superposition to process data exponentially faster than classical computers for specific types of calculations. Imagine solving a maze with 1,000,000 paths. While a classical computer takes one path at a time, a quantum computer can explore multiple paths simultaneously, dramatically reducing the time needed to find the solution. Unlike classical mechanics, which relies on deterministic outcomes, quantum mechanics is governed by probability. In quantum mechanics, we can only calculate the likelihood of a particle's behavior rather than predict a specific outcome. This probabilistic nature of quantum mechanics implies that we live in a world of chances at the smallest scales. To picture this, imagine rolling a die but never knowing which number will come up. Quantum mechanics allows you to know the odds but never the exact result in advance. This probabilistic view challenges the very notion of causality that is foundational to classical physics. While the principles of quantum mechanics may seem remote, they are at the heart of technologies like lasers, MRI machines, and semiconductors. The devices we use every day, from smartphones to computers, rely on the understanding of electrons and photons, which behave according to quantum laws. For instance, the flow of electrons in transistors, tiny switches in electronic circuits, can be explained only by quantum mechanics. Quantum mechanics has shown us that the universe is far stranger than we could have imagined, and we still don't fully understand it. It suggests a world where particles exist in superpositions, where uncertainty is fundamental, and where spooky connections challenge our understanding of reality itself. Despite its mysteries, quantum mechanics has proven to be one of the most successful scientific theories, predicting outcomes with incredible precision. The journey into the quantum world is ongoing, with physicists seeking a unified theory that merges quantum mechanics with Einstein's general relativity, a goal that could finally offer a comprehensive view of the universe. Quantum mechanics invites us to think beyond the limits of common experience, to see the universe not just as particles and waves, but as a complex, interconnected web of probabilities that continually reshape our understanding of reality. The uncertainty principle. Imagine you're trying to catch a bouncing rubber ball in a dark room. You can't see it, but you hear it hit different parts of the room. You reach out, guessing where it might be, but every time you try to catch it, it changes direction. In quantum mechanics, particles act a lot like that bouncing ball, except it's not just your vision that's blocked. There's a fundamental rule in nature preventing you from knowing certain things about the particle at the same time. This concept is called the uncertainty principle, first proposed by physicist Werner Heisenberg in 1927. The uncertainty principle suggests that, at a fundamental level, there is a limit to how precisely we can know certain pairs of properties about a particle, specifically its position and momentum. In other words, the more precisely we try to know a particle's location, the less we know about its momentum, and vice versa. This isn't about imperfect tools or methods. It's a fundamental property of the quantum world. To understand the uncertainty principle, think of a particle like an electron as a cloud of probabilities. In classical physics, we imagine particles like marbles. They have specific positions and velocities at any given time. However, in quantum mechanics, particles don't have exact locations until they're measured. Before measurement, they exist in a superposition of all possible positions and momentums, like a blurred photograph where nothing is fully clear. When we measure a particle's position very precisely, We effectively collapse its probability wave, forcing it to choose a specific location. But in doing so, we lose information about its momentum. If we try to measure the particle's momentum with high precision, we end up with less information about where it is. Unlike in the macro world, where limitations in measurement can often be solved with better tools, the uncertainty principle isn't due to technological limitations. It's built into the structure of quantum systems. When we measure a particle in quantum mechanics, we interact with it, typically by hitting it with photons or some form of energy. This act of measurement disturbs the particle, changing its properties. For instance, to measure a particle's position precisely, we might use high-energy photons. However, high-energy photons alter the particle's momentum, meaning the more accurately we locate it, the less precisely we know its speed and direction. So even our best efforts at precision run up against this fundamental barrier, a characteristic of all quantum particles. The uncertainty principle isn't just an oddity. It has far-reaching implications. It implies that the very notion of a deterministic universe, one where future events are entirely predictable from past ones, doesn't apply at the quantum level. Quantum systems behave probabilistically, and this principle is the core reason why the path of an electron around an atomic nucleus, for example, cannot be described as a neat orbit like planets around the sun. Instead, electrons exist in clouds of probability around the nucleus, where they are likely to be found. The principle also affects the energy levels within atoms. Since particles have a degree of uncertainty in their position and momentum, they cannot have zero energy. There's always a minimum amount of zero-point energy inherent in all particles. This is why atoms remain stable and don't collapse, as the uncertainty in an electron's position and energy keeps it from falling into the nucleus. One of the most fascinating phenomena that emerges from the uncertainty principle is quantum tunneling. Imagine a ball rolling up a hill. In classical mechanics, if the ball doesn't have enough energy, it will roll back down. But in the quantum world, particles can tunnel through barriers they seemingly lack the energy to cross, thanks to the uncertainty in their position and energy. Quantum tunneling is a crucial process in nuclear fusion in stars and forms the basis of modern technologies like the transistors and computers. The uncertainty principle is challenging because it defies our everyday experience. It forces us to rethink what it means for something to exist with specific properties. In our daily lives, we expect objects to have well-defined positions and velocities, like cars on a highway or planets in orbit. Quantum mechanics, and the uncertainty principle in particular, reveal that on the smallest scales, reality isn't as concrete. Particles are both here and there, fast and slow, clear and blurred all at once. Werner Heisenberg's principle reshaped physics, inspiring debates about the nature of reality itself. In fact, it led to the development of the Copenhagen interpretation of quantum mechanics, which suggests that particles exist as probabilities until measured. This interpretation essentially says that measurement shapes reality, that particles choose a state when observed, an idea that still prompts philosophical and scientific debate today. The uncertainty principle has redefined how we understand the limits of knowledge in physics. It shows that uncertainty is not a flaw in our understanding or our technology, but a built-in feature of the universe at the quantum level. Particles are not like marbles. They are like waves, fields of possibilities that collapse only when we observe them. This principle isn't a problem to be fixed. It's a fundamental aspect of how the universe operates, giving rise to the complex, fascinating behaviors of quantum systems. So when we look at the uncertainty principle, we are not just learning about the limitations of measurement, but uncovering a deeper truth about the fabric of reality. A universe where, at its most fundamental level, nature is as much about the unknown as it is about what can be known. Quantum entanglement. Imagine two identical twins separated at birth. Years later, each goes on to live a very different life, one in a bustling city, the other on a quiet island. Now imagine that, no matter the distance, each twin somehow feels what the other experiences, as if there's a mysterious thread connecting their lives. This idea captures the essence of quantum entanglement, a phenomenon so strange that Albert Einstein famously called it spooky action at a distance. Quantum entanglement is a principle that describes how particles, once entangled, become deeply linked such that the properties of one instantaneously influence the properties of the other, even if separated by vast distances. In the quantum world, if two particles are entangled, measuring one particle's state reveals the state of the other instantly, no matter how far apart they are. This concept strikes at the core of quantum mechanics and challenges our most fundamental understanding of space, time, and causality. To understand entanglement, let's start with particles in a special quantum state. In classical physics, we can easily measure properties like position, velocity, or spin for each object individually. But in quantum mechanics, particles can exist in superposition, where they simultaneously hold multiple states at once, sort of like a coin that is both heads and tails until we look at it. Now suppose two particles, say two electrons, are created together in such a way that they become entangled. Electrons have a property called spin, which can be imagined as a type of rotation and is often measured as spin up or spin down. When entangled, the electron spins become correlated in a way that, even if they're separated by galaxies, knowing the spin of one particle automatically tells you the spin of the other. If you measure one particle and find it to spin up, the other, no matter how far away, will instantly be found to be spin down. The particles are like quantum twins. They share a state that is intertwined. One of the most mystifying aspects of entanglement is that it appears to defy the speed of light, which according to Einstein's theory of relativity is the ultimate speed limit. If two entangled particles are on opposite ends of the universe, measuring one instantly affects the other. This seems to suggest that information somehow travels faster than light between them. But in quantum mechanics, entanglement doesn't rely on traditional communication between particles. It's not that one particle is sending a signal to the other. Rather, their states are interdependent from the moment of entanglement. Think of it as if both particles are sharing a single unified wave function, a mathematical description of their quantum state. When you measure one, the entire wave function collapses, meaning the state of the entire system becomes known instantaneously. This strange property of entanglement was famously challenged by Einstein, Boris Podolsky, and Nathan Rosen in 1935, who argued that quantum mechanics might be incomplete. They proposed what's now known as the EPR paradox, suggesting that if quantum mechanics allowed for this kind of instant correlation, it might be missing some hidden variables that would restore locality and determinism. However, experiments, especially those inspired by physicist John Bell and his Bell theorem, have repeatedly confirmed that quantum mechanics predictions hold true. These experiments show that no hidden local variables can explain the observed correlations. Entanglement is real, and it's non-local. Quantum entanglement isn't just a theoretical curiosity. It's at the heart of emerging technologies like quantum computing, quantum cryptography, and quantum teleportation. Quantum computers harness entanglement to perform complex calculations far more efficiently than classical computers. Entanglement-based cryptography promises ultra-secure communication that cannot be hacked without detection. And quantum teleportation, while not moving matter instantly, transfers the quantum state of a particle from one location to another, using entanglement as a resource. Entanglement forces us to rethink the fundamental nature of reality. It suggests that particles are not isolated, independent objects, but part of a deeply interconnected whole. Measurements here can affect outcomes there, not by transmitting signals, but by revealing the holistic nature of the quantum state. This challenges our classical intuition about separateness and independence. It invites us to consider a universe where connections transcend space, where what happens in one place is fundamentally linked to what happens elsewhere. Einstein may have been uncomfortable with the spooky nature of entanglement, but modern physics embraces it as one of the most intriguing and essential features of the quantum world. Entanglement has redefined what it means for particles to be separate. It shows us that at the deepest levels, the universe is not a collection of independent parts, but a web of relationships, a network of connections that defy our everyday experiences of distance and isolation. Entanglement is a vivid reminder that reality, at its most fundamental, is stranger and more wondrous than we could have imagined. The holographic principle. Imagine standing in a room and looking at a hologram, a two-dimensional surface that creates a fully three-dimensional image. As you move around, the image seems to shift and deepen, giving the illusion of depth and space, even though it's all encoded on a flat surface. The holographic principle in physics suggests something similarly mind-bending about the universe itself. It proposes that all the information in our seemingly three-dimensional universe may actually be encoded on a two-dimensional surface. This idea, although abstract, arose from a pressing problem in theoretical physics that involved black holes. In the 1970s, physicists Jacob Bekenstein and Stephen Hawking noticed a peculiar relationship between black holes and entropy, the measure of disorder or information contained in a system. Bekenstein proposed that the entropy of a black hole isn't proportional to its volume, as one might expect, but instead to the area of its event horizon, the boundary beyond which nothing can escape. This discovery was shocking because it suggested that the information describing everything that falls into a black hole could be encoded on its surface area, not its volume. This is where the holographic principle begins to emerge. In the 1990s, physicists Leonard Susskind and others took this idea further. They proposed that the same principle that applies to black holes might apply to the entire universe. In other words, all the information in our seemingly three-dimensional universe could be encoded on a distant two-dimensional boundary, much like how a hologram stores a 3D image on a flat surface. Just as a hologram creates the illusion of depth, our universe might be an illusion of three dimensions projected for lower dimensional reality. This idea is deeply tied to string theory, one of the leading candidates for a theory of everything. String theory attempts to describe the fundamental constituents of the universe, not as point-like particles, but as tiny vibrating or strings. In certain versions of string theory, the holographic principle naturally arises as a feature of the theory. In this framework, space and time themselves are emergent properties woven together from more fundamental, lower-dimensional information. The implications of the holographic principle are profound and perplexing. If our universe is a projection from a lower-dimensional realm, it challenges our very understanding of what it means to exist in space and time. The objects we perceive as solid and real may be, at their core, an encoded representation on a distant cosmic boundary. But does this mean our everyday experiences are merely illusions? Not exactly. Much like a hologram provides a realistic representation of an object, the three-dimensional world we navigate feels real because the encoded information is so richly detailed. The atoms that make up our bodies and the stars in the sky may be encoded on a cosmic boundary, but they still behave according to the laws of physics we observe in our familiar everyday world. One of the most exciting aspects of the holographic principle is that it could provide a framework for resolving some of the biggest puzzles in physics. In particular, it offers a possible solutivity, the theory that governs the very large. By viewing space-time itself as an emergent property from a more fundamental holographic description, the principle hints at a deeper unity between these two pillars of physics. While experimental confirmation of the holographic principle remains elusive, its theoretical foundation is robust, and physicists continue to explore its implications. For example, in 2017, researchers discovered hints of holographic duality in simple models of quantum entanglement, providing indirect support for the principle. Additionally, tools from holography have been used to study the behavior of quantum systems, giving rise to new insights into both condensed matter physics and the nature of gravity. In conclusion, the holographic principle stands as one of the most profound and speculative ideas in modern physics. It challenges our fundamental understanding of reality, suggesting that the universe we experience may be a projection from a lower dimensional boundary. While the idea remains largely theoretical, its potential to unlock deeper insights into the nature of space-time and information continues to inspire physicists to push the boundaries of human knowledge. Whether or not the holographic principle turns out to be a true description of the universe, it offers a tantalizing glimpse into the depths of the unknown, reminding us that reality is often stranger than we can imagine. The Multiverse Theory. The Multiverse Theory suggests that our universe is just one of countless others, each with its own set of laws, dimensions, and properties. Imagine this. What if, instead of just one universe that arose from the Big Bang, there are many, perhaps an infinite number, each with its own version of reality, its own physics, and perhaps even its own versions of us? This idea forms the basis of multiverse theory, one of the most fascinating and speculative concepts in modern physics. The multiverse theory isn't just a recent science fiction idea. It has roots in the study of cosmology and quantum mechanics. In the early 20th century, physicists like Hugh Everett and Niels Bohr struggled with the strange behavior of particles at the quantum level. When you observe a particle, it seems to choose one state, but before observation, it can exist in multiple states simultaneously, a concept known as superposition. Hugh Everett took this concept further with his many worlds interpretation, suggesting that when a particle takes on one of its many possible states, all other possibilities also occur, but in separate parallel universes. From there, the multiverse theory grew, fed by developments in cosmology, string theory, and theoretical physics. Today, physicists explore the idea of the multiverse in various ways, each suggesting a unique mechanism that could produce multiple universes. There isn't just one way to imagine a multiverse. There are actually several main types proposed by physicists, each bringing its own perspective on how these alternate realities might come to exist. Bubble universes or eternal inflation. Imagine that the Big Bang wasn't a unique event. In this version of the multiverse theory, space is like an inflating balloon, and within this ever-expanding cosmic bubble, smaller bubbles continuously form. Each bubble represents a separate universe with its own physical properties, separate from ours. Some might have entirely different laws of physics. Others might be quite similar. This concept comes from inflation theory, which describes the rapid expansion of space in the early universe. Alan Guth and Andre Linde, pioneers of this idea, suggested that inflation might not end uniformly across space, but instead create patches or bubbles, each becoming its own universe. The many worlds. Interpretation. Rooted in quantum mechanics, this theory suggests that every time a quantum decision is made, every time a particle has multiple paths it can take, the universe splits to accommodate each outcome. For example, if you're faced with a decision, each possible choice might exist in a different universe. This interpretation suggests that there are infinite versions of you, making every possible decision in every possible way, each leading to a different universe. The many worlds. Interpretation is one of the most popular in pop culture, often imagined as a kind of cosmic branching tree of choices and events. The brain multiverse. In string theory, our universe might be a brain, short for membrane, floating within a higher dimensional space known as the bulk. Other brains could coexist in the bulk, representing parallel universes just a small distance away in higher dimensional space. If these brains occasionally interact or collide, it might even explain phenomena like the Big Bang. Mathematical multiverse. Physicist Max Tegmark proposed that all possible mathematical structures exist in their own universes. In this view, mathematical equations and physical laws define realities, and each set of these mathematical rules could describe its own universe. In this mathematical multiverse, any structure that can exist mathematically does exist as a separate reality. Imagine a vast library with endless aisles. Each book on the shelves tells a different story, yet all are variations on certain themes. Some books contain stories almost identical to the one you're living now, while others diverge wildly. Some are tales of universes where stars are different colors, where gravity works differently, or where life never developed at all. This library represents the multiverse. Each book is a self-contained universe with its own narrative, each as real as the others, but with its own unique properties. Another analogy might be the surface of a pond with countless bubbles forming and popping. If each bubble is a universe, some form and grow, developing into full-fledged cosmoses with galaxies and stars. Others might collapse before reaching a mature state, while still others continue to float along, coexisting, yet never touching. The multiverse theory isn't just a whimsical idea. It offers potential answers to some of the biggest questions in physics. One major question is why our universe's conditions are just right for life. Physicists call this the fine-tuning problem. The constants that define our universe, like the strength of gravity or the speed of light, appear to be tuned precisely to allow stars, planets, and life to form. If any of these constants were slightly different, life as we know it wouldn't exist. The multiverse theory provides an explanation for this fine-tuning. In an infinite sea of universes, each with different constants, it's not surprising that some happen to have conditions favorable for life. We just happen to be in one of those universes. The multiverse theory remains highly speculative, and testing it presents a significant challenge. By definition, other universes are separate from ours and might be undetectable. However, scientists are exploring potential indirect evidence. Some hypothesize that gravitational waves or cosmic background radiation might show traces of interactions between our universe and others. Others suggest that experiments in quantum mechanics might eventually offer clues supporting the many worlds interpretation. Still, proving the multiverse's existence is a daunting task. For now, the multiverse remains a thrilling frontier, an idea that pushes the boundaries of what science can address. Whether real or imaginary, the multiverse expands our sense of possibility, suggesting that reality may be far vaster and more varied than we ever thought. The multiverse theory invites us to imagine an endless tapestry of realities, each with its own unique version of physics, existence, and perhaps even consciousness. Whether or not we ever prove its existence, the concept of the multiverse reminds us of the depth and mystery inherent in the cosmos, and that just beyond our visible horizon, there may lie an infinity of unknown worlds waiting to be discovered. String theory. Imagine you have a violin. When you draw the bow across the strings, they vibrate to create different musical notes. The pitch depends on the string's tension, thickness, and how it's played. Now imagine that instead of particles being point-like dots with no size or shape, they are like tiny vibrating strings. The vibration of the string determines the particle's properties, such as its mass and charge, just as a violin string's vibration determines the sound it makes. This is the central idea behind string theory, one of the most ambitious attempts in physics to explain everything in the universe with a single, unifying framework. String theory suggests that all fundamental particles, electrons, quarks, photons, and even gravity itself, are actually tiny loops or segments of string vibrating at different frequencies. Each vibration mode represents a different particle. What appears to us as different types of particles are just different notes played by these fundamental strings. String theory wasn't dreamed up in a day. It has its origins in the 1960s, when physicists were trying to understand the strong nuclear force that binds protons and neutrons in the nucleus. They noticed patterns in the data that suggested a string-like model. But it was in the 1970s and 1980s that string theory really took off as a candidate for unifying all the forces of nature. One of the reasons string theory is so attractive is that it naturally includes gravity. In other quantum theories, gravity doesn't fit easily. It resists being quantized like the other forces. But in string theory, one of the vibration modes of the string corresponds exactly to a particle called the graviton, which carries the gravitational force. This feature suggests that string theory could finally merge quantum mechanics and general relativity into one coherent theory of everything. String theory also predicts that the universe has more dimensions than the four we experience: 3 of space, 1 of time. In most versions of string theory, there are 10 or even 11 dimensions. But if these extra dimensions exist, where are they? Physicists suggest that the extra dimensions are compactified, curled up so tightly that they are invisible to us, like a garden hose that appears one-dimensional from a distance, but reveals a circular dimension when you look closely. The shape of these extra dimensions profoundly affects the properties of our universe. Different ways of curling them up can lead to different physical laws, particle properties, and even fundamental constants. This idea is part of what makes string theory both fascinating and challenging. It offers a vast landscape of possible universes, each with its own laws of physics, a concept that even connects to multiverse theories. String theory also led to the development of M-theory, an extension suggesting that strings are actually one-dimensional slices of more complex, multidimensional objects called branes. In this framework, our entire universe could be a three-dimensional brane floating in a higher dimensional space. Other branes might coexist in this space, representing parallel universes just beyond our perception. Imagine sheets of paper stacked closely together, each one a separate universe, occasionally touching or interacting. Such collisions between branes could even explain events like the Big Bang. One of the most important developments from string theory is holographic duality, also known as the ADS-CFT correspondence. This is a mathematical discovery showing that a theory with gravity in a certain kind of space can be equivalent to a quantum field theory without gravity on its boundary. This duality supports the holographic principle, suggesting that all the information within a region of space can be described by information on its boundary. The holographic duality has become a powerful tool for physicists. It offers new ways to study quantum gravity, black holes, and even complex systems like condensed matter physics. Despite its beauty and mathematical elegance, string theory remains unproven. It makes predictions at energy scales far beyond what current particle accelerators can reach. Testing it directly is enormously difficult. Nonetheless, string theory has provided profound insights into the nature of space, time, and information. It suggests that space-time itself is not fundamental, but emergent, woven together from the vibrations and interactions of strings and branes. String theory also offers a rich mathematical framework that has solved previously intractable problems in physics and mathematics, even outside its original goals. Critics argue that its vast landscape of solutions makes it hard to pin down specific, testable predictions about our universe. Supporters counter that it offers the most promising path toward unification we've ever seen. Whether string theory turns out to be the final theory of everything, or simply a stepping stone to an even deeper understanding, it has reshaped our view of the cosmos. It encourages us to imagine a universe far stranger and more intricate than anything our senses can detect. A universe of hidden dimensions, vibrating strings, and vast landscapes of possibility. As research continues, string theory remains one of the most fascinating and ambitious chapters in humanity's quest to understand the fundamental nature of reality. Dark matter and dark energy. When you look up at the night sky, you see stars, planets, and galaxies, all shining brightly against the darkness. But what if I told you that everything you see, the entire collection of stars, gas, dust, and planets, makes up less than 5% of the universe? The rest is invisible. This unseen portion is dominated by two mysterious components, dark matter and dark energy. Together, they account for about 95% of the total content of the cosmos. Let's start with dark matter. Physicists first suspected its existence in the early 20th century while studying the motion of galaxies. They noticed something strange. When they measured the speeds at which stars orbit within galaxies, they found those stars were moving much faster than could be explained by the visible matter alone. According to Newtonian gravity, galaxies should fly apart at these speeds. Yet they don't. They hold together. This discrepancy led scientists to propose that there must be additional mass that doesn't emit or interact with light. This invisible mass is what we call dark matter. It doesn't glow, reflect, or absorb light. It only interacts through gravity. Think of dark matter as an invisible scaffold holding galaxies together. Without it, galaxies would not have enough gravitational glue to keep their stars bound in rotating spirals. Dark matter is also essential in shaping the large-scale structure of the universe. When we look at simulations of cosmic evolution, including dark matter leads to the formation of the cosmic web, a vast network of filaments and voids that matches observations of how galaxies are distributed. But what is dark matter made of? That remains one of the biggest mysteries in physics. It might consist of hypothetical particles like WIMPs, weakly interacting massive particles, or axions, but so far these particles have eluded detection. Experiments around the world are trying to capture evidence of dark matter, from underground detectors to particle colliders. Despite decades of searching, dark matter has never been directly observed. Yet its gravitational effects are so compelling that most scientists believe it must exist in some form. Now let's turn to dark energy, even stranger and more mysterious. While dark matter holds things together through gravity, dark energy seems to do the opposite. It pushes the universe apart. The discovery of dark energy came in the late 1990s, when astronomers studying distant supernovae found that the expansion of the universe wasn't slowing down due to gravity as expected. Instead, it was accelerating. This shocking observation suggested that some unknown force was driving galaxies apart faster and faster over time. Physicists name this mysterious force dark energy. We don't know what dark energy actually is. One idea is that it's a property of space itself, often called the cosmological constant. In Einstein's general relativity, he originally included a cosmological constant to allow for a static universe, but abandoned it when expansion was discovered. Ironically, the cosmological constant turned out to be a useful idea for explaining the accelerating expansion. Another possibility is that dark energy is due to a dynamic field called quintessence, which evolves over time. Or it could be a sign that our understanding of gravity needs to be revised on cosmic scales. Despite the uncertainty, dark energy is a dominant force in the universe. It makes up roughly 68% of the total cosmic energy budget. Dark matter accounts for about 27%, while normal, visible matter, the stuff that makes up stars, planets, and us, makes up only 5%. The presence of dark energy has profound implications for the fate of the universe. If dark energy continues to drive accelerated expansion, galaxies will drift ever farther apart. Over billions of years, stars will burn out, galaxies will fade from view, and the universe could become a cold, dark, empty place. This scenario is known as the Big Freeze. Alternatively, if dark energy's properties change over time, even more exotic outcomes are possible. Some models predict a big rip, where the repulsive force grows so strong that it eventually tears apart galaxies, stars, planets, and even atoms themselves. Understanding dark matter and dark energy is one of the biggest challenges in physics and cosmology. Despite knowing they dominate the universe, we don't know their fundamental nature. Observatories, telescopes, and experiments around the world are searching for clues. Projects like the James Webb Space Telescope, the Euclid mission, and the Vera C. Rubin Observatory aim to map the distribution of dark matter and measure the effects of dark energy with unprecedented precision. Physicists also hope that discoveries at the Large Hadron Collider or other particle experiments might reveal the particles that make up dark matter. While these mysteries remain unsolved, they remind us of the humbling truth that most of the universe lies beyond our current understanding. Dark matter and dark energy represent the hidden majority of the cosmos, shaping its evolution and fate in ways we are only beginning to grasp. They challenge us to expand our scientific horizons and explore the unknown. They invite us to keep asking questions, to keep observing, to keep pushing the boundaries of human knowledge. And they remind us that, for all we have learned, there is still so much left to discover in this vast and beautiful universe. The Big Bang Theory. Look up at the night sky. Every star you see is moving away from us. Not just the stars, but entire galaxies, rushing outward in all directions. This observation leads us to one of the most profound ideas in cosmology, the Big Bang Theory, the Big Bang. Theory is the leading explanation for the origin and evolution of the universe. It states that the universe began as an extremely hot, dense point roughly 13.8 billion years ago and has been expanding ever since. This doesn't mean the Big Bang was an explosion in space. Instead, it was an expansion of space itself. To imagine this, think of the surface of a balloon covered with dots representing galaxies. As you inflate the balloon, the dots move away from each other. not because they're flying through space, but because space itself is expanding. This analogy helps us understand that the universe isn't expanding into anything. Space itself is stretching, carrying galaxies along with it. The evidence for the Big Bang theory is strong and multifaceted. One of the key observations supporting it is the cosmic microwave background radiation, CMB. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, this faint glow fills the entire sky. It is the cooled remnant of the intense heat from the early universe, now just a few degrees above absolute zero. The CMB is like a baby picture of the universe, showing it as it was about 380,000 years after the Big Bang. Before this time, the universe was so hot and dense that atoms couldn't form. Instead, it was a plasma of charged particles and photons. As the universe expanded and cooled, electrons combined with nuclei to form neutral atoms. This moment, called recombination, allowed light to travel freely, creating the cosmic microwave background we observe today. The CMB isn't completely uniform. It has tiny temperature variations that reveal the seeds of all future structure in the universe: galaxies, stars, and planets. These fluctuations are a cosmic fingerprint of the quantum ripples that were stretched during the universe's inflationary period. Inflation is a critical extension of the Big Bang theory. It proposes that in the first tiny fraction of a second after the Big Bang, the universe expanded exponentially faster than the speed of light. This rapid inflation smoothed out the universe and explains why the cosmic microwave background is so uniform while still containing small variations. Inflation also helps explain why the observable universe appears flat and why regions so far apart have similar properties, despite being causally disconnected. Another pillar of evidence for the Big Bang is Hubble's law. In the 1920s, astronomer Edwin Hubble observed that galaxies are moving away from us, and that their speed is proportional to their distance. This relationship means the universe is expanding, which directly supports the idea that it was once much smaller and denser. If we run the expansion backward in time, we reach a point of infinite density and temperature, the singularity, where the known laws of physics break down. While the Big Bang theory explains the expansion of the universe from this hot, dense state, it does not tell us what caused the Big Bang itself or what came before it. That remains one of the deepest mysteries in cosmology. Some theories suggest the universe could have emerged from a quantum fluctuation. Others propose cyclic models, where the universe goes through endless cycles of expansion and contraction. Still others invoke the multiverse, where our Big Bang is just one bubble in an endless sea of universes. While the Big Bang theory doesn't answer every question, it is incredibly successful in explaining a wide range of observations. For example, it predicts the relative abundances of light elements like hydrogen, helium, and lithium. These predictions match what we see in the oldest stars and in primordial gas clouds, providing strong evidence for Big Bang nucleosynthesis, the process that forged these elements in the universe's first few minutes. It also offers a framework for understanding the large-scale structure of the cosmos. Galaxies and galaxy clusters formed as matter clumped under the influence of gravity, tracing out a vast cosmic web shaped by the tiny fluctuations we see in the CMB. As our observational tools have improved, we've continued to refine the Big Bang model. Telescopes like the Hubble Space Telescope and missions like Planck have given us incredibly detailed maps of the cosmic microwave background. These maps allow scientists to measure fundamental properties of the universe, such as its age, composition, and geometry, with remarkable precision. The Big Bang theory also accommodates the presence of dark matter and dark energy, even if their exact nature remains unknown. Dark matter helps explain how galaxies formed and stayed bound together despite their rapid rotation. Dark energy explains why the universe's expansion is accelerating. Together, these components shape the past, present, and future of the cosmos. The Big Bang theory represents one of the most profound shifts in human understanding. It tells us that the universe had a beginning, that it has evolved over billions of years, and that it continues to change today. It invites us to see ourselves as part of an ongoing cosmic story, a story that began in an unimaginably hot, dense state and has led to the formation of galaxies, stars, planets, and life itself. Cosmic inflation. Imagine blowing up a balloon. At first, it's tiny, but as you keep blowing, it expands rapidly, growing larger and smoother. This simple analogy helps us understand cosmic inflation, one of the most important ideas in modern cosmology. Inflation is a theory that proposes the universe underwent an extremely rapid expansion in the first tiny fraction of a second after the Big Bang. This expansion was not just fast, it was exponential, meaning the universe doubled in size repeatedly in unimaginably short intervals. The concept of inflation was introduced in the early 1980s by physicist Alan Guth. It was designed to solve several puzzles left unexplained by the original Big Bang theory. One of these puzzles is the horizon problem. When we look at the cosmic microwave background radiation, the afterglow of the Big Bang, we see that it's almost the same temperature in every direction. But according to standard Big Bang expansion, regions on opposite sides of the sky should be so far apart that they never could have exchanged information or energy. How did they become so uniform? Inflation solves this by suggesting that, before inflation, the universe was small enough for all regions to come into thermal equilibrium. But then inflation stretched this tiny uniform patch to cosmic scales, explaining why the observable universe appears so smooth and consistent. Another puzzle inflation addresses is the flatness problem. Observations show that the universe is very close to geometrically flat. But without inflation, the Big Bang model suggests it would have to have been incredibly fine-tuned to be so flat today. Inflation explains this by expanding space so much that any initial curvature is flattened out, just as the surface of an inflating balloon appears flatter the larger it gets. Inflation also helps explain the absence of magnetic monopoles, hypothetical particles predicted by some theories, but never observed. By stretching the early universe, inflation would have diluted any monopoles to undetectable levels. But perhaps the most remarkable aspect of inflation is how it connects quantum and cosmic scales. During inflation, tiny quantum fluctuations, minute variations in energy, were stretched to astronomical sizes. These fluctuations became the seeds for all structure in the universe. After inflation ended, these slight over and under densities in matter grew under gravity to form galaxies, stars, and planets. When we observe the cosmic microwave background, the slight temperature variations we see are a direct imprint of these primordial quantum fluctuations. Inflation thus provides a mechanism for explaining how the universe's large-scale structure emerged from the quantum realm. The idea of inflation has received strong support from observations, particularly detailed measurements of the cosmic microwave background. Experiments like the Planck satellite have confirmed that the patterns of temperature fluctuations match the predictions of inflationary models. However, while inflation is a highly successful theory, it's not the final answer. Physicists are still working to understand how inflation started and ended, and what kind of field or mechanism drove it. One popular model involves a hypothetical particle called the inflaton, which would have dominated the energy density of the early universe and caused the rapid expansion. As the inflaton field decayed, inflation ended, reheating the universe and leading to the conditions described by the standard Big Bang theory. Inflation also opens the door to eternal inflation, a scenario where inflation never stops entirely, but continues in some regions of space. In this view, our observable universe is just one bubble in an ever-inflating cosmic foam, each bubble potentially becoming its own universe with its own physical properties. This idea connects naturally to multiverse theories, suggesting that inflation might be the mechanism that produces a vast ensemble of universes. Testing the details of inflation remains one of the biggest goals in cosmology. Researchers look for specific patterns in the cosmic microwave background, such as B-mode polarization, that could provide evidence for primordial gravitational waves generated during inflation. Such discoveries would offer even more compelling confirmation of the inflationary paradigm. Despite its challenges and mysteries, inflation remains a cornerstone of modern cosmology. It provides a simple yet powerful explanation for the universe's large-scale uniformity, flatness, and structure. And it connects the tiniest scales of quantum physics to the vastness of cosmic evolution. Inflation is a reminder of the universe's profound and sometimes counterintuitive beauty. It suggests that the largest structures we see today grew from the smallest imaginable fluctuations, that the entire observable universe once fit into a region smaller than an atom. And it invites us to consider a cosmos far grander and more varied than we can easily comprehend. A cosmos where even the unimaginable might be possible. Black holes. Imagine a place where gravity is so strong that nothing, not even light, can escape its pull. A region of space where the known laws of physics break down and time itself slows to a crawl. This is the realm of black holes. Black holes are among the most fascinating and mysterious objects in the universe. They are regions of space-time where gravity has become so intense that it forms a boundary known as the event horizon. Once anything crosses this boundary, there is no return. It is trapped forever, drawn inevitably toward the black hole's core, or singularity, where density becomes infinite and our current understanding of physics ceases to function. But how do black holes form? Most black holes are born from the death of massive stars. When such a star exhausts its nuclear fuel, it can no longer support itself against the pull of gravity. Its core collapses inward, compressing matter into an incredibly dense state. If the collapsing mass is great enough, it will form a black hole. This process leaves behind an invisible object that can only be detected through its gravitational effects on nearby matter. Black holes aren't cosmic vacuum cleaners sucking in everything indiscriminately. Objects can orbit a black hole safely at a distance, just as planets orbit stars. It's only when something crosses the event horizon that escape becomes impossible. One way astronomers detect black holes is by observing accretion disks, hot, glowing rings of gas and dust spiraling into the black hole. As this material accelerates and heats up, it emits powerful X-rays that telescopes can detect. Black holes also reveal themselves through their gravitational influence on nearby stars. By tracking a star's orbit, astronomers can infer the presence of an unseen, massive companion. One of the most famous examples is a supermassive black hole at the center of our own Milky Way galaxy. Astronomers have observed stars whipping around an invisible object with over 4 million times the mass of the Sun. In 2019, the Event Horizon Telescope collaboration released the first ever image of a black hole's shadow, located in the galaxy M87. This striking picture showed a bright ring of light surrounding a dark central region, the shadow of the event horizon. It provided stunning confirmation of Einstein's general relativity and offered humanity its first direct glimpse of a black hole's edge. But black holes aren't all the same. They come in different types and sizes. Stellar mass black holes are formed from collapsing stars and typically have masses a few times that of the Sun. Intermediate mass black holes may form through the merger of smaller black holes or through the collapse of massive star clusters. These are harder to detect, and their existence is still an area of active research. Supermassive black holes lie at the centers of galaxies, with millions to billions of solar masses. Their origins remain mysterious, though they likely grew over time by consuming gas, dust, stars, and merging with other black holes. Some galaxies even have quasars, incredibly bright centers powered by supermassive black holes, consuming matter at astonishing rates. The process releases so much energy that quasars can outshine entire galaxies. At the smallest scale, theorists have speculated about primordial black holes, tiny black holes that might have formed shortly after the Big Bang due to extreme density fluctuations. While none have been detected, they remain a possible explanation for certain cosmic mysteries, including some forms of dark matter. Black holes are not eternal. Physicist Stephen Hawking showed that black holes can slowly evaporate through a quantum process now known as Hawking radiation. Virtual particle pairs constantly appear and annihilate in empty space. Near the event horizon, one particle might fall in while the other escapes, effectively stealing energy from the black hole. Over incredibly long timescales, this process causes the black hole to lose mass and eventually vanish. For stellar mass black holes, this evaporation would take far longer than the current age of the universe. But it offers a remarkable bridge between quantum mechanics and general relativity, two theories often at odds. Black holes also pose one of the deepest puzzles in physics, the information paradox. According to quantum theory, information about a system's initial state cannot be destroyed. Yet if something falls into a black hole and the black hole later evaporates, what happens to that information? Does it disappear forever, violating quantum principles? Or is it somehow encoded in the Hawking radiation, or preserved in some other way? Physicists continue to debate and study this mystery, with potential implications for a future theory of quantum gravity. For all their darkness, black holes illuminate our understanding of the universe. They test the limits of physics, offering clues about the unification of gravity and quantum mechanics. They power some of the brightest phenomena in the cosmos. And they invite us to imagine realms where space and time bend in ways that defy our everyday experience. Black holes remind us that the universe is a place of extremes and mysteries, regions where the known laws of nature give way to the unknown, challenging us to keep exploring, questioning, and reaching for deeper understanding. Time travel. Imagine stepping into a machine, pushing a button, and finding yourself in the distant past or far future. And the idea of time travel has fascinated humans for centuries, inspiring countless stories, films, and scientific debates. But is time travel really possible? And what does physics say about it? In everyday life, time seems straightforward. It flows in one direction, from past to present to future. We remember yesterday, experience today, and anticipate tomorrow. This arrow of time is closely tied to entropy, the second law of thermodynamics. Entropy tends to increase over time, creating a directionality to events. Eggs break but don't spontaneously reassemble. Coffee cools but doesn't heat itself back up. But when we look at the fundamental laws of physics, like Newton's laws or even quantum mechanics, they're mostly time symmetric. They work the same forward and backward. There's nothing in those equations that says time must flow in one direction. This symmetry suggests that, at least mathematically, traveling back or forward in time might not be impossible. Einstein's theory of special relativity introduced the idea that time is not absolute. Time depends on motion. For someone traveling close to the speed of light, time slows down relative to a stationary observer. This is called time dilation. Astronauts on fast-moving spaceships would age more slowly than people on Earth. In a sense, this is a form of time travel to the future. By moving quickly, one can leap forward relative to others. But what about traveling backward in time? Here things get even stranger. Einstein's general relativity describes gravity as the warping of spacetime. Solutions to Einstein's equations reveal that spacetime can be twisted in ways that allow for closed time-like curves, paths through spacetime that loop back on themselves. One famous example is the Gödel metric, discovered by mathematician Kurt Gödel in 1949. Gödel's universe is a rotating cosmos where time travel to the past is mathematically possible. Another concept is the wormhole, or Einstein-Rosen bridge. A wormhole is a hypothetical tunnel connecting two distant points in spacetime. If one mouth of the wormhole is accelerated close to the speed of light and then brought back, time dilation would cause it to age differently from the other mouth. This difference in aging could, in theory, allow for time travel between different eras. Travelers entering one mouth could emerge from the other at an earlier or later time. However, building or stabilizing a wormhole would require exotic matter with negative energy density, something we have yet to discover or create in sufficient quantities. Even if such matter exists, keeping a wormhole open and safe for human travel poses massive engineering and theoretical challenges. Physicists have also proposed other solutions like the Tipler cylinder, an infinitely long rotating cylinder that could twist spacetime enough to create closed time-like curves. But practical limitations, like needing infinite length, make these ideas more theoretical curiosities than engineering plans. Time travel also raises famous paradoxes. The most well-known is the grandfather paradox. If you travel back in time and prevent your grandfather from meeting your grandmother, you would never be born. But if you're never born, how could you travel back to prevent them from meeting? This logical loop seems to make time travel to the past impossible. Physicists and philosophers have proposed various solutions to these paradoxes. One idea is the Novikov's self-consistency principle, which suggests that any actions taken by a time traveler were always part of history. In other words, you couldn't actually change the past in a way that creates a paradox because your actions would have always been consistent with the timeline. Another idea is the many worlds interpretation, borrowed from quantum mechanics. If you change the past, you don't alter your original timeline. Instead, you create a new branching universe where events play out differently. This approach avoids paradoxes, but suggests that time travel to the past would involve hopping between different branches of a multiverse. Despite these intriguing theories, there's currently no experimental evidence that time travel to the past is possible, and many physicists suspect that some as yet unknown laws of quantum gravity would forbid it. Stephen Hawking even proposed a chronology protection conjecture, suggesting that the laws of physics prevent closed time-like curves from forming, thus protecting causality and avoiding paradoxes. Still, time travel remains a vibrant area of study. It challenges our understanding of causality, free will, and the very nature of time itself. And it continues to inspire physicists to explore the limits of general relativity, quantum mechanics, and any future unified theory of physics. Even if we never build a time machine, studying time travel pushes us to ask deep questions. What is time? Why does it have a direction? Is the past truly gone, or does it exist in some way? And could the universe allow journeys not just through space, but through time itself? These questions remind us that science isn't just about solving practical problems. It's also about exploring the deepest mysteries of reality, pushing the boundaries of imagination, and seeking to understand our place in the vast, complex, and beautiful cosmos, quantum gravity. At the heart of modern physics lies a stubborn puzzle. We have two extremely successful theories: general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which describes the behavior of particles at the smallest scales. But these two theories don't play nicely together. General relativity treats space-time as smooth and continuous, bending in response to mass and energy. Quantum mechanics, on the other hand, describes a world of probabilities, uncertainty, and discrete packets of energy. When physicists try to apply quantum principles to gravity, they encounter mathematical infinities and contradictions. This conflict has led to one of the greatest quests in theoretical physics: the search for quantum gravity. Quantum gravity is an attempt to unify general relativity and quantum mechanics into a single framework. It aims to describe how gravity operates at the Planck scale, the incredibly tiny distance of about 10 circumflex 35 meters, where quantum effects of space-time itself become important. At this scale, the smooth fabric of space-time might be replaced by a quantum foam, a churning, probabilistic sea of tiny fluctuations. But what would such a theory look like? Several competing ideas have emerged. String theory is one of the most famous candidates. Instead of treating particles as zero-dimensional points, string theory models them as one-dimensional vibrating strings. These strings can include a vibration mode corresponding to the graviton, the hypothetical quantum particle that carries the force of gravity. String theory also naturally includes extra dimensions, offering a framework where gravity and quantum mechanics might coexist peacefully. However, string theory is complex and difficult to test directly, and it predicts a vast landscape of possible universes. Loop quantum gravity is another approach. Rather than adding extra dimensions or strings, loop quantum gravity attempts to quantize space-time itself. It suggests that space is made up of tiny, discrete loops woven into a spin network. These loops give space a granular structure at the Planck scale. In this view, space-time isn't smooth but built from finite chunks, much like a fabric woven from individual threads. Loop quantum gravity preserves many aspects of general relativity while introducing quantum principles in a direct way. It has had successes in describing quantum aspects of black holes and in formulating cosmological models that avoid the Big Bang singularity. Another approach to quantum gravity involves causal dynamical triangulations, where space-time is modeled as a series of connected simplexes, like tiny tetrahedra, that grow and evolve according to quantum rules. By simulating how these building blocks assemble, physicists can study the emergence of space-time geometry from fundamental quantum processes. Asymptotic safety is yet another idea. It suggests that gravity might be safe from infinities at high energies because it approaches a fixed point in its behavior, much like how other forces in physics do. This would allow gravity to be described consistently in quantum terms without needing entirely new ingredients. One of the biggest motivations for quantum gravity comes from black holes. Classically, black holes have an event horizon and a singularity inside, a point of infinite density where the laws of physics break down. Quantum gravity is expected to smooth out or resolve these singularities, offering a more complete picture of what really happens inside black holes. Stephen Hawking's discovery that black holes emit Hawking radiation raises deep questions about information. If black holes evaporate over time, what happens to the information about everything they consumed? Quantum mechanics says information can't be destroyed. Resolving this black hole information paradox is expected to require a theory of quantum gravity. Another arena where quantum gravity is crucial is the Big Bang itself. According to classical general relativity, the universe began with a singularity of infinite density. But this is likely an incomplete description. Quantum gravity may reveal a more detailed, non-singular origin of the universe, perhaps replacing the singularity with a bounce or some other quantum phenomenon. Despite decades of effort, no single theory of quantum gravity has been universally accepted. String theory offers mathematical elegance and unification, but remains hard to test. Loop quantum gravity provides a more conservative, background-independent approach, but is less ambitious in unifying all forces. Other ideas continue to develop, each offering unique insights and challenges. Physicists also study holography, inspired by the ADS/CFT correspondence in string theory, which suggests that a quantum theory without gravity on a lower dimensional boundary can fully describe a gravitational theory in the bulk. This duality has given powerful tools for understanding black holes, quantum entanglement, and even the emergence of space-time itself. Ultimately, the search for quantum gravity is about reconciling two pillars of our understanding of the universe. It aims to explain how gravity behaves when quantum effects cannot be ignored, such as in the cores of black holes or at the birth of the universe. It may reveal that space and time are not fundamental but emergent from more basic quantum principles. And it promises to deepen our understanding of reality itself, showing us how the cosmos works at its most fundamental level. For now, quantum gravity remains one of the most exciting and challenging frontiers in physics, a grand puzzle that beckons the next generation of scientists to unravel its mysteries. Entropy and the arrow of time. Imagine watching a video of a glass falling off a table, hitting the floor, and shattering into countless pieces. Play the video in reverse and it seems absurd. The shards miraculously leap back together, forming a perfect glass. Why does time seem to flow only one way? Why do we remember the past, but not the future? These questions lie at the heart of the arrow of time. While the fundamental laws of physics are the time-symmetric, they work equally well forward and backward. Our everyday experience clearly distinguishes past from future. This asymmetry is deeply connected to entropy, a concept from the second law of thermodynamics. Entropy is often described as a measure of disorder or randomness. In any closed system, entropy tends to increase over time. It's why heat flows from hot to cold, why gases spread out to fill their containers, why organized systems tend to become disorganized. It's the reason your coffee cools down instead of heating itself up. The second law of thermodynamics doesn't forbid order. It just says that without external input, systems naturally evolve toward higher entropy. This increase in entropy gives time its arrow. In the glass example, the unbroken glass on the table is a low entropy state, a highly ordered arrangement of molecules. When it shatters, the pieces scatter into a higher entropy state with many more possible configurations. The laws of physics allow the reverse process, but it's so statistically unlikely that we never see it happen naturally. This statistical view of entropy was pioneered by Ludwig Boltzmann in the 19th century. Boltzmann recognized that entropy measures the number of microscopic ways a system can be arranged while still appearing the same macroscopically. A shattered glass has vastly more possible configurations than an intact one. Thus, systems evolve towards states with more possible configurations, higher entropy. But why did the universe start in such a low entropy state? After all, if entropy tends to increase, there must have been a time when it was very low. Cosmologists believe the early universe just after the Big Bang was in a state of remarkably low entropy. While it was hot and dense, matter and energy were distributed extremely evenly. Paradoxically, this smoothness corresponds to low gravitational entropy. Over time, gravity caused matter to clump, forming stars, galaxies, and black holes, structures associated with higher entropy. This initial low entropy condition is essential for explaining why time has a direction at all. Without it, the universe might be a chaotic, high entropy mess with no arrow of time. The increase of entropy over cosmic history explains why processes seem to have a preferred direction. Eggs break, but don't unbreak. Stars burn fuel and shine, but don't spontaneously reassemble spent fuel. Living organisms grow, reproduce, and eventually die, increasing entropy in the process. The arrow of time isn't just a human illusion. It emerges from the fundamental statistical properties of systems evolving from a low entropy beginning. Interestingly, the laws of physics don't dictate the direction of time. They allow processes in both directions equally. It's the boundary conditions of the universe, the fact that it started in such a low entropy state, that give rise to the asymmetry we experience. Entropy also plays a crucial role in information theory. Claude Shannon introduced the idea of information entropy, measuring the uncertainty or surprise in a message. Higher entropy means more unpredictability. This connection has deep implications, linking thermodynamic entropy with the storage and transmission of information. In the context of black holes, entropy takes on even more fascinating meanings. Jacob Bekenstein and Stephen Hawking showed that black holes have entropy proportional to the area of their event horizon. This Bekenstein-Hawking entropy suggests that the information about what falls into a black hole isn't lost, but somehow encoded on its surface area, a result that inspired the Holographic Principle. Hawking's discovery that black holes emit radiation due to quantum effects raised profound questions about the fate of information. If black holes evaporate completely, does the information about what fell in disappear forever? This black hole information paradox remains one of the most significant puzzles in theoretical physics, highlighting the need for a complete theory of quantum gravity. Entropy's role extends beyond physics to philosophy and the nature of life itself. Life seems to create order, building complex structures from simpler components. But it does so at the cost of increasing entropy in its surroundings. Organisms maintain low internal entropy by consuming energy and releasing waste, ultimately increasing the total entropy of the universe. Thus, the second law isn't violated but fulfilled. Even conscious experience is shaped by entropy. Memory relies on irreversible processes in the brain. We remember the past because traces of it exist in our minds and environment, created by entropy-increasing processes. We don't remember the future because those traces haven't been laid down yet. In this way, entropy doesn't just define physical processes, but underpins our very perception of time. In the grand scheme, entropy is both a limit and a guide. It constrains what's possible, making perpetual motion machines impossible, and ensuring heat engines can't be 100% efficient. Yet it also drives the evolution of complexity, structure, and life in a universe that began in a remarkably ordered state. As we continue to study entropy, we gain deeper insight into the fundamental nature of time, the origins of the universe, and the fate that awaits it. The arrow of time reminds us that change is inevitable, that creation and destruction are intertwined, and that the universe's story is one of unfolding possibilities, written in the language of entropy. The observable universe. When we gaze up at the night sky, we're looking out into an immense cosmic expanse. But even this grand vista represents only a tiny portion of the observable universe. The observable universe refers to the region of space from which light has had time to reach us since the Big Bang. Because the universe is about 13.8 billion years old, you might think this boundary lies 13.8 billion light years away in every direction. But that's not the case. Due to the expansion of space, the actual radius of the observable universe is about 46 billion light years. This expansion means the light we see now was emitted from regions much closer long ago, but those regions have been moving away ever since. Imagine blowing up a balloon with dots on its surface. As the balloon expands, the dots move farther apart. Even if light left one dot early on, the space between the dots has stretched dramatically, making the distance between them much greater now than when the light began its journey. The observable universe is a sphere centered on us. But every observer in the universe has their own observable sphere, centered on them. The cosmic horizon doesn't mark an absolute edge of the universe, but rather the limit of what we can currently see. Beyond this horizon lies more universe, perhaps infinite, forever hidden from view because light from those regions hasn't had time to reach us. Inside the observable universe are an estimated 2 trillion galaxies. Each galaxy contains hundreds of billions of stars, and many of those stars likely host planets. The sheer scale boggles the mind. Galaxies cluster together in vast structures called filaments, forming a cosmic web interspersed with enormous voids, regions of comparatively empty space. The largest known structures in the universe, like the Hercules Corona Borealis Great Wall, span billions of light years. Yet even these immense formations respect the cosmological principle. On the largest scales, the universe is homogeneous, the same in all places, and isotropic, the same in all directions. This principle is foundational to modern cosmology, years old. Tiny variations in the CMB's temperature encode the seeds of all future structure, the galaxies and clusters we see today. Observing these fluctuations has allowed scientists to infer crucial details about the universe's age, composition, and curvature. Cosmic expansion also shapes what we can see. As galaxies move away from us, their light is redshifted, stretched to longer wavelengths. The farther away a galaxy is, the faster it recedes, in accordance with Hubble's law. Beyond a certain distance, known as the cosmological event horizon, galaxies are moving away faster than light can reach us. Even if we waited forever, light from those regions would never arrive. This doesn't violate relativity because it's not objects moving through space faster than light. It's space itself expanding. The expansion of the universe means the observable universe changes over time. In the distant past, it was much smaller. Future observers will see a different cosmos. Because of dark energy, which drives accelerated expansion, distant galaxies will eventually recede so quickly that their light will no longer reach us at all. Over trillions of years, the night sky will empty. Future astronomers may see only their local group of galaxies, unaware of the broader universe we see today. Our current observations are thus uniquely privileged, a snapshot of a universe rich with information. Studying the observable universe helps us understand cosmic evolution. We see galaxies at different distances, and thus at different times in their histories. Some galaxies appear as they were billions of years ago. This look-back time allows us to reconstruct the universe's story. We see how galaxies form, merge, and evolve. We see the birth and death of stars. We witness the role of dark matter in shaping large-scale structure and the effects of dark energy in accelerating cosmic expansion. But the observable universe is just what we can see. It tells us nothing conclusive about the universe's total size or shape. Is the universe infinite, Does it loop back on itself in some higher dimensional topology? These remain open questions. Inflationary theory suggests the universe is much larger, perhaps infinite, far beyond what we can observe. Our cosmic horizon limits what's knowable. There could be regions with different physical constants or even entirely separate bubble universes, as suggested by some multiverse models. Despite these mysteries, the observable universe is an extraordinary laboratory. It gives us clues about the early universe's conditions, the fundamental laws of physics, and the universe's ultimate fate. It reminds us that even from our tiny vantage point on Earth, we can peer back across billions of years and billions of light years to uncover the story of the cosmos. The observable universe is a testament to human curiosity and ingenuity. It is both a boundary and an invitation, a limit to what we can see, but also a challenge to imagine what lies beyond. As we build better telescopes, launch more sensitive instruments, and refine our theories, we continue to expand the edges of this cosmic map, bringing the vast, ancient universe ever more vividly into view. In Cosmological Constant, imagine a universe that's expanding, but not slowing down as expected. Instead, it's speeding up, with galaxies racing away from each other, faster and faster over time. This accelerating expansion was one of the most surprising discoveries in modern cosmology, and it has revived interest in an old idea: the cosmological constant. The cosmological constant, often denoted by the Greek letter lambda, was first introduced by Albert Einstein in 1917. At the time, general relativity predicted that the universe should either be expanding or contracting. But the accepted view then was that the universe was static and unchanging. To make his equations allow for a static universe, Einstein added the cosmological constant, a term that provided a repulsive force balancing gravity's pull. However, in 1929, Edwin Hubble's observations revealed that the universe is actually expanding. Einstein reportedly called the cosmological constant his greatest blunder for trying to force the universe to be static. For decades, lambda was largely ignored. But that changed in the late 1990s, when two independent teams of astronomers studying distant type Ia supernovae discovered that the universe's expansion isn't slowing down, it's accelerating. This acceleration suggests that some unknown force or energy is counteracting gravity on cosmic scales. The simplest explanation is to reintroduce lambda as a cosmological constant, a form of energy inherent to space itself. Unlike matter or radiation, whose energy density decreases as the universe expands, the cosmological constant has a constant energy density. As space expands, new space forms with the same energy density, leading to an overall increase in total energy. This property makes lambda a natural candidate for dark energy, the mysterious component that now appears to make up about 68% of the universe's total energy budget. In Einstein's field equations of general relativity, the cosmological constant acts as a repulsive term, driving accelerated expansion. Mathematically, it can be seen as a simple addition to the geometry of spacetime, a term that curves spacetime in a way that opposes gravitational collapse. But what is the cosmological constant physically? One interpretation is that it represents the vacuum energy of empty space. According to quantum field theory, even the vacuum isn't truly empty. It's filled with virtual particles popping in and out of existence, creating a background energy. This vacuum energy could act like a cosmological constant. However, there's a huge problem. When physicists try to calculate the vacuum energy using quantum field theory, the result is 120 orders of magnitude larger than what's observed. This discrepancy is one of the biggest unsolved problems in theoretical physics, known as the cosmological constant problem. Why is the observed value so small, yet not exactly zero? Is there some mechanism that cancels most of the vacuum energy, but leaves a tiny residual value? No one knows for sure. Some physicists suggest that the cosmological constant might not be truly constant. Instead, it could be due to a dynamical field, often called quintessence, that evolves over time. Unlike a true cosmological constant, quintessence would have changing properties, potentially explaining variations in the expansion rate. Observations so far are consistent with a true cosmological constant, but future surveys may detect subtle differences that point to dynamical dark energy. Understanding lambda is critical because it determines the fate of the universe. If dark energy remains constant, the universe will continue expanding forever, with galaxies moving out of view, stars dying out, and space growing increasingly empty, a scenario known as the Big Freeze. If dark energy grows stronger over time, it could lead to a big rip, where the expansion accelerates without bound, eventually tearing apart galaxies, stars, planets, and even atoms themselves. Alternatively, if dark energy decays or reverses sign, gravity could regain dominance, potentially causing the universe to collapse in a big crunch. For now, observations suggest the expansion will continue accelerating indefinitely. Measurements of the cosmic microwave background, galaxy clustering, and supernova distances all support a flat universe with about 68% dark energy, 27% dark matter, and 5% normal matter. This composition is often called the LCDM model, lambda cold dark matter, the standard model of cosmology. Despite its success, the cosmological constant remains one of the greatest mysteries in physics. It challenges our understanding of gravity, quantum mechanics, and the very nature of space and time. It raises profound questions. Why does empty space have energy? Why is its value so small yet non-zero? Is it truly constant, or does it change? Could it be evidence of new physics beyond our current theories? Einstein introduced lambda to keep the universe static, only to discover the universe had other plans. Now lambda is back, not as a mistake, but as a crucial ingredient explaining one of the most remarkable discoveries of the 20th century. The universe is not just expanding, but accelerating. The cosmological constant is both a term and an equation, and a window into the deepest mysteries of the cosmos. It reminds us that space itself isn't an empty void, but a dynamic, active player in the universe's grand story. And it challenges us to keep exploring, to seek the fundamental truths hidden in the fabric of space-time itself. The Anthropic Principle. Why does the universe seem so perfectly tuned for life? Why do the fundamental constants of nature have values that allow stars to shine, planets to form, and chemistry to flourish? These questions lead us to one of the most debated ideas in cosmology and philosophy, the Anthropic Principle. The Anthropic Principle is the idea that the laws and constants of the universe must allow for the existence of observers like us, because if they didn't, we wouldn't be here to notice them. At first glance, this might sound like a tautology or even a trivial statement, but it has profound implications for how we understand the universe. There are different forms of the Anthropic Principle. The weak Anthropic Principle simply states that our observations of the universe are conditioned by the fact that we exist in it. For example, if the gravitational constant were much stronger, stars might burn out too quickly for life to evolve. If it were weaker, stars might never ignite. We observe the gravitational constant to be what it is, because only such a value allows observers to exist. In this sense, our existence filters the range of possible universes we could observe. It's not that the universe was designed for us, but that only a universe with certain properties could contain beings capable of asking these questions. The strong Anthropic Principle goes further. It suggests that the universe must have properties that allow life to develop at some stage. Some interpretations even suggest that the universe is in some sense compelled to bring forth observers. This idea verges on teleology, the notion that the universe has a purpose or goal, which makes many scientists cautious about embracing it. The Anthropic Principle becomes especially interesting when combined with the idea of a multiverse. If our universe is just one of countless others, each with different physical constants, then it's not surprising that we find ourselves in one where the conditions happen to allow life. Most universes in this ensemble might be sterile, chaotic, or short-lived. But in the rare universes where the constants align just right, life can evolve and ask questions. In this view, our universe's fine-tuned properties don't require a special explanation. They are simply the result of selection bias. We exist in this universe precisely because it permits our existence. This multiverse-based version of the Anthropic Principle has been used to address problems like the cosmological constant problem. Why is the cosmological constant so small but non-zero? If it were much larger, the universe would expand too quickly for galaxies to form. And if it were negative and large, the universe would have collapsed quickly after the Big Bang. In a multiverse of many possible values, only those with suitable values for lambda would produce galaxies, stars, and life. So we naturally find ourselves in such a universe. Critics argue that the Anthropic Principle, especially in a strong form or when combined with the multiverse, isn't really a scientific explanation. It doesn't predict specific values for constants, but rather explains them after the fact. It risks becoming unfalsifiable, since we can't observe other universes to test whether they have different constants. Some see it as a philosophical statement rather than a scientific theory. Nonetheless, the Anthropic Principle has real predictive power in certain contexts. For example, physicist Brandon Carter, who coined the term Anthropic Principle in the 1970s, used it to predict the age of the universe we should expect to observe. He argued that intelligent observers would only arise during a narrow window in a star's lifetime. Such reasoning has been used to explore astrobiological questions about the likelihood of life around different types of stars. In physics, Steven Weinberg used anthropic reasoning to predict an upper bound for the cosmological constant before its small positive value was discovered. His argument was that lambda couldn't be much larger than it is, or a galaxy formation would be impossible. This prediction was later seen as a success of anthropic reasoning. In philosophy, the Anthropic Principle raises questions about observation selection effects. It forces us to consider how our position as observers shapes the data we see. We can't assume our vantage point is typical in an absolute sense. We must account for the fact that any observation is conditioned by our existence as observers in specific environments. Ultimately, the Anthropic Principle is a tool for framing questions about fine-tuning in physics and cosmology. It doesn't necessarily imply design or purpose, but reminds us that any explanation must account for our presence as observers. It invites us to think carefully about what we can and cannot infer from our observations. And it underscores a profound truth. Our understanding of the universe is inevitably shaped by the fact that we are part of it, not apart from it. The Anthropic Principle, in its various forms, continues to provoke debate and inspire new lines of inquiry. It sits at the intersection of physics, philosophy, and even metaphysics, challenging us to reflect on the conditions that make existence and understanding possible. Conclusion. Physics is not just a set of equations and theories. It's a story, a grand narrative that seeks to explain where we came from, what the universe is made of, and how everything works. From the earliest days of Newtonian mechanics, when we learned to predict the motion of apples and planets, to the revolutionary ideas of relativity and quantum mechanics, our understanding of nature has continually deepened and evolved. We've discovered that time and space are not rigid stages on which the universe plays out, but flexible, dynamic entities that can bend, stretch, and even warp into black holes. We've learned that matter and energy are two forms of the same thing, that mass can curve space-time, and that the speed of light sets an ultimate limit on how fast information can travel. We've ventured into the quantum realm, where particles behave like waves, exist in superpositions, and become entangled across vast distances in ways that defy classical intuition. Quantum mechanics reveal that uncertainty is not just a limitation of our instruments, but a fundamental feature of reality itself. Our journey took us to the beginning of time, to the Big Bang, when the universe was unimaginably hot, dense, and small. We've seen how cosmic inflation stretched tiny quantum fluctuations into the seeds of galaxies, and how the universe expanded and cooled to form the cosmic microwave background, the oldest light we can observe. We've mapped the distribution of dark matter, an invisible scaffold shaping the formation of galaxies and clusters. We've discovered that most of the universe's energy lies in a mysterious dark energy that's accelerating its expansion. We've confronted questions about the cosmological constant, vacuum energy, and the possibility of a multiverse with regions where physics takes on different forms. We've pondered the nature of black holes, where space-time folds in on itself so tightly that not even light can escape, and where quantum mechanics and gravity collide in paradoxes that challenge our understanding. We've imagined the ultimate fate of the cosmos, whether it ends in a big freeze, a big crunch, a big rip, or some other unimaginable scenario. We've explored the idea that entropy gives time its direction, shaping the arrow of time that leads from the ordered past to a more disordered future. We've recognized that our observations are conditioned by our own existence, the Anthropic Principle, forcing us to think carefully about what we can know and why the universe seems so finely tuned for life. We've even dared to ask whether time travel is possible, if wormholes could connect distant arrows, or if the universe could allow journeys not just through space, but through time itself. Yet, for all we've learned, the universe remains full of mysteries. What is dark matter made of? What is dark energy really? How can we unite general relativity and quantum mechanics into a single coherent quantum gravity theory? What happened before the Big Bang? If that question even makes sense. Is our universe just one of many in a vast multiverse? Are space and time fundamental, or do they emerge from even deeper principles? These questions don't signal failure. They are invitations. They are the frontiers of human knowledge, places where our theories falter and the unknown beckons. They remind us that science is not a finished edifice, but an ever-growing, ever-changing exploration of reality. Physics is not about having all the answers. It's about asking the right questions, building models that explain what we observe, and pushing those models to their limits to see where they break. It's about embracing uncertainty, challenging assumptions, and remaining open to the possibility that nature may be stranger, more beautiful, and more profound than we can currently imagine. In this journey, we rely on mathematics as our language and experiments as our tests of truth. We build telescopes to see the faintest light from the edge of the observable universe. We smash particles together to glimpse the fundamental building blocks of matter. We simulate cosmic evolution on supercomputers and test gravity's limits with exquisitely sensitive instruments. We collaborate across borders and generations, sharing ideas and data, refining theories, and celebrating discoveries. And through it all, we maintain a sense of wonder. Because ultimately, physics is not just about understanding the universe out there. It's also about understanding ourselves. We are the universe made conscious, matter that has learned to ask questions about its own origins and fate. We are stardust contemplating the stars. We are ephemeral beings seeking timeless truths. And though our lives are brief, our curiosity is boundless. The universe may one day end in heat death or rip itself apart. But for now, it is alive with structure, energy, and possibility. It is a place where galaxies swirl, stars shine, planets form, and life emerges to look up and wonder. Physics gives us the tools to explore these wonders. It teaches us humility in the face of the unknown and courage to keep seeking answers. It is, in its deepest sense, a celebration of our capacity to know, to imagine, and to connect with the cosmos that gave birth to us. So let us continue to study, to learn, to question. Let us keep building our models of the universe, knowing they will be revised, challenged, and improved. Let us remain curious, even in the face of uncertainty. Oh, because that curiosity is one of our greatest gifts, a flame we can pass on to future generations. In the grand story of the cosmos, our chapter is still being written. And physics is one of the ways we give that story meaning. Thank you for listening. Thank you for joining us on this journey through the cosmos. We hope these hours spent exploring the wonders of physics have inspired a sense of curiosity, awe, and reflection. Whether you're drifting off to sleep or simply relaxing, know that you're part of a long human tradition of looking up at the stars and asking, why? Physics isn't just for scientists in labs or mathematicians at blackboards. It belongs to all of us. It's the story of everything, from the tiniest particles that flicker in and out of existence to the vast clusters of galaxies that stretch across the universe. It's the language we use to describe falling apples, orbiting moons, and the swirling dance of galaxies. It's the framework that lets us send spacecraft to other planets, harness the power of atoms, and gaze deeper into space and time than ever before. But most of all, it's a testament to human curiosity, the same spark that lit the fires of our ancestors, urging them to wonder about the lights in the sky, burns in us today. That spark has taken us from myths and stories to equations and experiments, from guessing at the shape of the Earth to landing probes on distant worlds. It has taught us that the universe is vast, ancient, and filled with mysteries, that it follows elegant, knowable rules, but also defies our intuitions, that it can be described by mathematics, but remains rich with wonder. We've seen that the universe is dynamic, expanding, evolving, that time has an arrow, driven by entropy, that space itself can warp and bend, giving rise to black holes and gravitational waves, that matter is energy, and energy is matter, that particles are waves and waves are particles. That observation itself plays a role in shaping reality at the quantum level. We've confronted the mysteries of dark matter and dark energy, which together make up most of what exists. We've glimpsed the possibility of other universes, of extra dimensions, of a multiverse beyond our own. We've asked whether time travel is possible, whether the universe will end in heat death, a big crunch, or something stranger. And in all of this, we've found that every answer leads to new questions. This is not a flaw in science, but its greatest strength. Science is a conversation with the unknown, a way of forever expanding the boundaries of what we can see, know, and imagine. As you close your eyes tonight, remember that you are made of the same elements forged in ancient stars, that the atoms in your body were once part of suns that lived and died billions of years ago, that you are, in a very real sense, the universe becoming aware of itself. Your thoughts, dreams, and questions are not separate from the cosmos. They are expressions of it. So stay curious. Keep asking questions. Keep wondering about what lies beyond. Because in doing so, you're participating in one of the oldest and most beautiful traditions of our species, the tradition of seeking knowledge, of telling stories about how the world works, of building models, testing them, and revising them, of trying to understand our place in this vast and magnificent universe. The journey of physics is far from over. New discoveries await. New mysteries beckon. And you, yes, you are part of that adventure. Because the universe doesn't just belong to physicists or astronomers or mathematicians, it belongs to all of us, to everyone who has ever looked up at the night sky and felt wonder, to everyone who has asked why. So thank you for listening. Thank you for wondering. Thank you for being part of this grand, ongoing quest to understand the universe and our place within it. Good night. Sleep well, and dream of stars.